Okay, so today we're going to talk about digital workflows, and I start off with a question that I probably don't need to ask, but why do we use computers? Um, I mean, this is an online class, so everyone's going to be using a computer right now, so it shouldn't be that big of a thing to answer. But let's go more deeply into what computers are useful for, at least in what we're doing. Um, Hold on, let me see if I can fix. Okay, so we use computers for a couple things. One, I'm going to start with computerization. So there's and oh, so we do things to automate tasks, right? Like AutoCAD and drafting. The fundamental differences in drafting in AutoCAD and drafting with a pencil are not that extreme, right? Pencil becomes your mouse. You draw straight lines in 2D for the most part. You're automating that task a little bit through different processes on the computer, but it helps you do the same sort of thing. You can store and access data such as Excel. It easily allows you um, to keep track of a large amount of data. Obviously, computers are good at that. Um, you guys have probably never had to balance a checkbook before, but the people that probably your parents did. Um, people that do that had to keep track of everything that they did. Now computers do that for you, so it makes things a lot more streamlined. We can focus on other things. So we can speed up common tasks. So when we use Adobe, when we use word processing, that allows us to say instead of typing on a keyboard, we can type on the computer. We don't have to like white out things that we mess up, and so our day becomes a lot easier as our task become easier. Um, and then in terms of like BIM, we have a lot of possibilities for error checking and coordination. So that's one of the whole points of BIM is that all this information is coordinated together, and we can see if there's anything that might conflict with that. These processes that we use computers for computerization all require the input of knowledge. They require that you know what's going on, that you have the information that you're feeding to the computer, and the computer helps you with that. And it also requires you understand the outcome sort of beforehand. You don't have to know the specific answers, like if you're using like a Excel spreadsheet to add something up or what have you, but you do know what's happening. You're just using the computer to sort of help you do that task. And so that's sort of like taking that task and putting it into a computer. Pretty streamlined. We use computers a lot for that. Now the other side of that is computation, and so that's what we kind of want to focus more on. We'll do a lot of computerization in this class as well, but computation is something a little different. There's slight distinctions between that. So we would use computation for, say, simulating things, which might be like physics or computational fluid dynamics. Um, we can use it for the generation of form, which might be for parametric architecture or algorithmic modeling. We can use it for analysis, so environmental or structural analysis to sort of get information out of sort of our models to understand them a little more, or to iterate multiple times, to to do a simple step over and over again that leads to more complex information. And so that might be evolution or machine learning, things that we program the computer to do, that help us, develop more knowledge than we've plugged into it. So those are helpful because the computer is giving something back to us. We're not just providing the computer with all information, but somehow it becomes um, a collaborative process of computing and making decisions and designing and doing all the things that we need. So that enables our designs to become a little smarter. That becomes enables us to sort of have some co-agency with the computer. We're still developing the processes for things to happen, so it's not completely removed from the person, but somehow these more I don't want to call them evolved design decisions, but give you more information to make those decisions along the way. So computation is useful in that respect. On top of that, we also have things like visualization, specifically for our field. That's very important. Quick, fast sketches and ideation, sort of rendering out photorealistic diagrammatic views, and documentation plans and construction sets. And those fall into various forms of computerization or computation, depending on how you're using it. Then we also have more experience with things like AR, VR, that we won't get into in this class, but are becoming more prevalent in the field. Okay, so let's take a look at a few sort of digital workflows. So this is a workflow diagram of a practicing architects in and so this is just one of the many possible setups for how a firm might work. This is one that they put together of all the different sort of softwares and how they interact and what they use them for. But it's a good sort of like overall layout of the different things that an architect can do and probably will do in the process of designing and getting a building finished. So you can see that there's several different workflows highlighted with those boxes. So there's computational or complex geometry workflow that we'll focus a lot on in the first part of this class. There's presentation workflow that you sort of use all the time. A documentation workflow, that's where Revit comes in a lot, or AutoCAD. A fabrication workflow that may or may not be within the hands of the architect. If architects are now building more and more these days parts of their projects, especially at a small scale, so often those things get pretty streamlined, or as a way of translating information to the people that are fabricating it. And then you have, those are all the kind of the ones in green. The ones in gray are related to architecture, but maybe more consultants or construction administration side of things. So you have analysis workflow that would be looking at environmental analysis or structural analysis, things like that. Then you have 4D, 5D workflow or file management. That's really construction administration, making sure the project is organized, and cost analysis for things, and sort of organizing the construction in different ways. And so look at this and ask yourself kind of where you want to be in the future in your sort of design studies, what you want to do as a designer or an architect sort of moving forward. Architecture may or may not be the end goal. You can do a lot of things with an architecture and design degree. So you might even tend to specialize in some of these. Whether you want to be a project manager, you're probably more in this like file management, 4D, 5D sort of workflow sort of situation. Construction administration is in there as well. You might be a drafts person, which is less common as a very specific career choice, but pretty common in terms of straight out of school, like what you might be working on, developing the drawing side of things or the documentation side of things. There are visualization specialists. if you're pretty good at rendering or making drawings or diagrams or things that represent the projects, there are architects that specialize just in that, and they're often working on, say, like the competition teams and things like that, quickly cranking out those visualizations to get projects, or for client benefit to visualize things in the future. Or there's possibilities for being consultants. A lot of architects work as consultants, especially in sort of the analysis workflow or even the complex geometry workflow. Though a lot more architects are having those as sort of standard skills inside their offices nowadays. Several architects, Norman Foster, Zaha, or other larger firms will have specific groups. SOM, Maged was part of the sort of advanced modeling, black box at SOM, where they were looking at developing new tools and workflows for computational design in those offices. And so there's a lot of potential opportunities depending on what you get good at and what do you sort of like focus your expertise on. So keep that in mind with all these ideas of software that you're learning throughout school. I'll show you some potential ways, and other people will show you other ways. But you can sort of determine your own sort of path depending on what you are more interested in. And I would also add that you can. I would only get an expertise in something if you're really interested in it, because often you can get pigeonholed into that task. So if you're a good renderer, sometimes you might render solely. So keep those things in mind as well. So we're going to cover, like I said, we're going to cover a lot of these in the class. And we're going to look at that complex geometry workflow. We'll get into sort of the interoperability with Revit, down with V-Ray. You guys should be pretty familiar with Photoshop and Illustrator, things like that you've worked on before. Not all of these, I mean, this diagram is already a couple years old, 2012, so a lot of these have already sort of phased out. Things like Ecotech is no longer a thing. A lot of other workflows are sort of updated into new softwares that become easier to use or more available. Generative components is I think rarely used. Grasshopper is much more common now with that. And so you have to remain sort of flexible with these things. Get an understanding of how things work, but don't be fixed to that, because things change all the time. So you need to be able to adapt along those as well. Okay, so let's look at a few. We'll dive into our complex geometry. We'll look at a couple of Grasshopper sort of processes to understand how to use it a little bit more. So we went over the interface last week. We'll go over a couple ways to use it, and I usually start with math sort of operations. Everyone should be pretty familiar with math and how to do it, though it can get more complicated. So we can use Grasshopper in pretty simple ways that we're familiar with. Common math operations: plus, minus, additions, multiplication, division, things like that, just like a normal calculator. And we would sort of plug numbers in. You can see how that works with the A and B numbers that you're adding together. And we can use a panel to visualize what that answer is, right? You should probably understand and be able to visualize that pretty well. The two inputs, the function in the middle, and the outputs that come out of that. We won't do examples of those sort of things. Then we have other ones that you may or may not be familiar with. Simple things like Boolean operations. So If I were to ask you a yes or no question, something like if we have a list of numbers over here on the left, are each of these numbers greater than or smaller than, say, 10? So is it is it is it greater than 10, let's say, or less than 10 in this case that's on the screen? And then you would give me an answer. You would say yes it is, no it's not, this is true, this is false. That's a Boolean answer. There's only one of two choices. It's very very black or white. It's true or false. It's ones or zeros. Those all mean the same sort of things and can be used interchangeably. So in this the answer that comes out of this is a bunch of trues, right? Or in some case there's a couple falses as well. The 10 and the 25 are not less than 10, right? 10 is equal to 10 and 25 is greater than 10. So you get a couple answers that come out. And so we can take that list and say use that true false values to then split it up. This is a dispatch, and we can say, okay, this list, these are all the ones that are true, they are less than 10, and these are all the ones that are false, that are not less than 10. And then we have also sort of logic gates like that negate that. All the ones that are true, we can run it through here and they become false. So those are useful at organizing data in a little bit if we need to use those. And then we can set maximums and minimums. You know, all of these numbers, we can say, is it what's more, these numbers or some other number that we're feeding into? We'll say 17.3. When most of these cases, except for 25, the 17.3 is going to be the maximum number. Or if we can use the minimum, most of them are going to be smaller than 17.3. So we can use that to set maximum minimums in value sets. And then one that you probably haven't seen that much is a modulus. And that's pretty useful. It's a little like division. And it's, if you're going to divide two numbers, it's going to give you not the result, but the remainder. So you can say 9, oh, let's look at, yeah. 9 is the fourth one on this. 9 divided by 2 will give you the answer, but the remainder is going to be 1 because it's an odd number, right? You divide anything by 2, you get either an even 0 or an odd number of 1. What did Madison says? What did you say the component was called? Which one? This dispatch up here? Sorry, I made the diagrams and I didn't have the names on. So this is called a dispatch. We'll use that a little bit later on. Look at the chat a little bit. So Justin and Johnson are having trouble joining the class.
Johnson just did.
Johnson just did. What about Justin?
I'm trying to text him now.
Okay. You guys yeah. Work on that. I'll keep going.
Did you get down?
Okay. Oh, modulus. Yeah. So this is modulus. It looks like a percent sign. And that's pretty useful for determining if things are even or odd if you divide them by 2, but you can really use any number that you divide it by and it'll give you the remainder. Okay. Oh, this one. And then we also have, we can plug in any number of math functions, simple things like averages. You can see the average of all these numbers is 6.8 for what that's worth. And then we can also plug in, if we don't have the specific function as a component, we can make that math function with one of these two components. Both of these are a function and an expression component, where we can plug in, say, the square of any number. next to the 2, so that's 6.8 will give you that answer, or we can plug it in like this. And we can have any number of variables that we plug into it. So that can be useful if you're making a mathematical surface or trying to define specific parabolas or things like that. That could be useful in some respect. And then we can also sort of tailor these things more to what our needs are. So say we want to find the average, but we want some numbers to be more important than other numbers. We can kind of skew the average result by their weights. So we can say we have 10 numbers over here, and we can give a weight for each number. We can say, okay, the 5 has no weight, so it's not going to do anything to this average. Maybe some of these other numbers are weighted higher or lower. And so this will actually adjust that average by adjusting how much these numbers control the average, which is really interesting. That's not typically a math function that we use, but it would be really useful in terms of geometry. You can see the picture here is kind of these 3 points with a point in the center. If you think of finding the average point, you could actually push this point around by using the average. And we'll maybe run through an example of that in Rhino as well. And one that we use all the time, and we'll go into Grasshopper and try some of these in a second, is remapping numbers. So say you have the same set of numbers, and you want them. You can almost think of them in like grades. These would not be very good grades, but if you wanted to map these from, in this case, 0 to 1 or 0 to 100 if it's a percentage of something, you can say what is this number within that sort of range, right? So what you can do is you can get a bounds. So that bounds will tell you what the highest and lowest number. The lowest number is going to be 0. The highest number is going to be 25. So that's the minimum and the maximum of all of these numbers, right? So if you've ever curved or seen grades curved, that's kind of how it would work. You would say, okay, these are the minimum grade in the class is the maximum grade in the class. Whoever has the highest grade sort of scoots up to 100 or some percentage that you set up. And so you can say, okay, these numbers that are from 0 to 25 is going to be the original range, and you're going to set it from 1 to 0. So 0 still stays 0. 25 becomes 1 because that's the new maximum, and then everything else is proportional within that. So we'll use that quite a bit and often for different things. Let's quickly take a look at some of those. I'm gonna open up. I'm gonna need to sign on to the VPN real quick. Sorry, I tried to open a file that wasn't connected, and so it crashed my Rhino. But on Canvas, you should have those example files. Okay, so let's take a look at some of these. So this is an example of a remap where we have these numbers. We have some sort of value between 0 to 25 that we are remapping these to a value of 0 to 1. So exactly the example that we had on the slide. Now, how can we use this? Let's try to think of an example. I'm going to plug these values in first. Say I have a curve, and I'm going to evaluate that curve. We'll get into that a little bit more on Wednesday of what that means, but it's basically putting points at these various numbers along this curve. So if you think of this being 0 and this being 1, all of these values sort of mapped across that curve give you these sort of values. Now we can also adjust that so it's not so linear. If we run these through a graph, we can sort of change their proportions even more specifically, spread them out. So this is essentially remapping those numbers again into different sort of values. You can see the 1 and the 0 sort of always stay the same, but the scale in between those gets sort of skewed a little bit. Bifocals, yeah. So this is a graph mapper, and if you right click on that, you can have any number of ways of looking at that. Parabola, which actually the lower end of it becomes 1, scoops down and then back up, and so these numbers actually come down and then back, or actually up, down, and then back up. So that's slightly different. Gaussian curvature. So they can be useful for a lot of things. I think the one I use the most is the sort of Bezier curve. I'll actually talk about that a little bit more on Wednesday as well. Okay. So you don't have to use just the numbers, but they can be used more for geometric operations as well. The Boolean values that I mentioned before, where you can say take these values and dispatch them true or false, right? So this splits in different ways. You can also say if you have points and distances, you can set up, if a distance to a point is less than this, then you can split it out, and we'll use that a little bit later in class as well. Here's the modulus that I mentioned. So if I change this to be 3 or 4, you can see the remainders change quite a bit. So it's less informative of of even or odd numbers, but it can still be useful if you want to see if something is a multiple of 4. It's going to be a 0. Everything else is not going to be a multiple of 4. That's also useful for these Boolean values. Anything that's a 0 is going to be considered false. So if you have some number, even if it's like 4, 2, or 1, if it's divisible by 5, it's going to be, in this case, a false value. If it's not divisible by 5, then it's going to be a true value. So you can say anything that's false is going to be a multiple of 5 in that respect. So that can be useful for different purposes. Um, the extra examples I gave you sort of go in. Somebody have a question? No. The extra examples I gave you go into a little bit more of using functions, creating functions to generate geometries, or specifically more like surface or array patterns. We won't go into those, but you can see you use all kinds of things that can be useful. The same sort of commands like the modulus and percentages and absolute values. Everything can be sort of found here um, if you need it. And you can sort of look at those examples more specifically for a tutorial on that. We won't get into it though. And these, I want to show an example with the points and weights. So I'm gonna make 10 points. I think that's 10. I should have done it in this, but okay, so I'm going to bring these points into this. Instead of using this number, I'm going to use these point locations, right? So if I turn this on, this should be an average point of all of these. And each one of these weights refers to one of these points. So if I want to turn down the value of that one, that's going to be this first point. Let's look at what those points actually are. If I use a point list, I can see that okay, so this is the 0th point in that list. This is the 0th point in that list. So if I take this 0 point and turn that down, it's no longer going to pull it in that direction, right? Same with these. If I take the 0, 1, 2, I can adjust the weight of that and pull it in that direction or not. So this is essentially, in this case, almost like gravity, right? I can make the pull stronger or smaller, weaker, whatever, to adjust how these points are affecting things. So that middle point sort of moves around. It's not the positional average. It's somehow position times however strong it is. So that's also a fairly useful sort of tool for things. Okay, let's go back and look at list management. Did I close that? Okay, so list management. So one of the key ideas in Grasshopper is sort of organizing your data. So I think I said before, if you understand how to organize your data and make sure that things are lining up how they're supposed to, that solves 90% of your problems in Grasshopper. So we're going to go over more specifically how to do that. So if you have a list, there's certain operations that you'll use all the time. If say you have this, it could be a list of numbers, it could be a list of geometry, whatever it is. If you want to do certain things, say you want to shift that list. If we had this list of numbers and we wanted to like move it left or right, so the 0th item or the last item was not at the ends of the list, but somehow they were shifted to the middle and the other ones sort of wrap around. You could shift it by 3 points or 3 spaces, and all of those would sort of like move down. If you wanted to get one specific item out of that list, you could say this 3 is no longer a shift of 3 items, but you can just say the 3rd item in the list. And remember when we said the 0th item, the first item in the list is not 1. The first item in the list is 0. It always starts counting for some reason in computation, because computers like it more, to start counting with 0. So the 0 is the first item in the list. So the 3rd item in the list is actually 4th in the list, not to be confusing. But it's not the way we normally count. It's the way computers count. So 0, 1, 2, 3 would be that item in the list. Then you have things like if you wanted to split a list, right? You want to split it by a specific index. So if we wanted to say 0, um, 0 through 3 is in one list, and then anything above that is going to be in a second list. Or I'll have to check and see if it goes 0 to 2 and then 3 is in the upper list or the lower list. But it's going to split those into two separate lists so that if you needed to do one thing with one list and another thing with another list, you can control what data goes where. If you remember from our last sort of class, you can't just select on your geometry, right? If it's in Grasshopper, it's sort of in Grasshopper, it's not selectable. So if you wanted to separate out specific lines for things, then you have to do that more explicitly through your tools rather than selecting on it. So if you want to say all the high numbers or all the you could sort a list of lines by their length, and you can get all the numbers above this are going to be the longer lines or something like that. Okay, so you have those sort of operations for sort of moving and selecting items out of the list. You can also do something similar, but removing items from the list, not sort of removing everything else. Like if you were going to select the item, you wanted that one item, all the rest of them will go away. If you wanted to take that item out of the list, you can use some of your cull patterns, or cull in general just means to remove things out. So you can do that in different ways. You can use your booleans again as a pattern. So if it's a cull pattern, it's going to take this true false value. Anything that's true is going to output. Anything that's false, or I might have it backwards, I'll have to see. Anything that's false is gonna not output it. So it'll repeat that pattern. So if you have 3 items over here, but your list is 100 items long, it's gonna repeat that pattern and take every third one. All right, so that would be a good way of pulling out specific items, and that can be something that has three items in that list that repeats, or you can have a true false value for every item in the list. Right. So if you were if you had some geometry and you said you were measuring the length, you say, is this length longer than 10? It would give you a true false value for every one of those lines. And then you can use this the same way you did. I was using the dispatch to say, I want to keep some of these and I want to get rid of some of those. I can use that true false value to keep all the ones that meet a criteria that I'm looking for. Same thing with cull index. If you wanted to remove the third item in the list, you could use that by an index. And then one that's fairly similar but a little less controlled is a random reduce. If you have, say, 100 items in a list and you wanted to sporadically get rid of some population of them, however many, you say, okay, I'm gonna get rid of 3 of these at random. The computer will randomly select 3 and get rid of them. So randomly reduce that. You can actually set that up by number or by a percentage. You can say if there's 100 items in the list, 100 times some sort of percentage. Say you want to get rid of 90% of them, it's going to get rid of 90 of them, right? Okay, so those are pretty useful for different reasons. We'll try to use those occasionally as well. And then there's situations where you want to align data to other data. If you have 2 lists, say you want to draw lines from one point to another, but you have lists of points. So every item in the list is going to draw a line to another item in another list. All right? So that's useful, so you don't have to draw 100 line items. You can sort of just make 2 lists of points and connect them all together. So the first item in the first list and the second item in the second list are going to connect. Right? And then, sorry, the first item and the first item, the second item, the second item, the third item, and third item, they're all going to sort of respectively connect But if those lists are different lengths, then some funny stuff happens. So let's take a look and see what that actually is. Where's okay, so turn these off real quick. So say you have, these are two random lines that I've drawn and just imported into this. Or actually, let's start from scratch. You can follow this around. Okay, so I'm gonna draw two random lines. And, whatever. Two lines like that, right? I can import those lines. This will be the top one. This will be the bottom one. Now, if I want to divide those lines, I can say divide curve, and I'll divide both of them by some number, and I'll put my bifocus on. Okay, so this gives me the same number of points. Maybe I'll make that a little different. Let's say 10 points in this one. And so we can adjust those separately. Now I can make a line between those. And since we have list of points, the first list and the second list are going to connect relatively simply like that. All right? Well, if they're not the same number of points, if I turn this down to 5, all of a sudden you get some weird stuff happening where that last point is trying to connect to the rest of those. Because those lists are uneven, it still's trying to connect. It wants to connect those 10 to some number. So it's gonna say repeat that last number until all the connections are done. So that may or may not be what I want, right? So I need some way of adjusting those to suit what I want to do. So you can use some of those. You can say the longest lists might be a way of doing this. I plug the A and the B into that. It's going to repeat the last in this case, which should give me the exact same thing. But I have other ways of doing it. I can say repeat first, and so the first one will repeat before it goes on to the next one. Or maybe more useful would be interpolate. So depending on however many there are, it's going to sort of evenly distribute those. So you don't have to do math and figure out which ones connect to which ones. Or wrapping would say instead of repeating the last, it will jump and these will now sort of start over and repeat. Now that's interesting because that's more like the shift that we were talking about. If I were to make this 10 again, plug this in here, or I can just leave that. And I say shift the list. That's almost identical to what was happening before, right? So we're basically aligning these points. Now I'm going to turn some numbers on so you can see what that looks like. This is the point list of this one. The point list of that one. Okay, so we have some numbers for these, and you can see right now if it's shifted 0, it has 0 to 10, 0 to 10. Now if I shift that one, you can see that 0 is actually starting to count right there, up to 6, and then loops back around. So the 7th item is always connected to the 7th item. The 5th item is always connected to the 5th item, no matter where it is. Right? So if I can rearrange this list, I can get different points to connect where I want. Does that make sense? Yeah, maybe. Okay, so we can also use other sort of operations. We can say, let's scoot this down. We can say if we wanted to pick just one item out of this list to connect to. Now we have 10 items. I'm going to pick the 4th one. We're going to use that. So you can see this 4 is connecting to all of them. I can do that independently. Now, there's a W down here, and the W is for wrapping. So right now, if I go above 10, it's going to start over. So if I were to say, okay, I can go up to 20, it'll just repeat that. So the 15th item in the list is just that sort of repeated over till it gets to that point. Same thing with the shift list. You can have a true false value if you're shifting it. If I were to plug this back in with that shift, right now it repeats over. If I set that boolean to false, then it'll just go to the end and it won't keep shifting back to the beginning. So keep in mind the subtle differences in those as we move forward, because they become really, really useful for organizing and pulling out data in different ways. Okay, so let's do another example, and I'm going to use the example. So I haven't showed you much of my work. You may have seen it in like a presentation or two. There's this project where we had to make these cells that we wrapped in carbon and glass fiber, right? Which are essentially just a bunch of points that we're wrapping around. So as maybe an architectural example, we can do things fairly similar to this, where we say, we'll go to perspective instead. If I draw a couple of polylines, whatever these things look like, I'll make them slightly different just to illustrate kind of the point. And these weren't even planar, so some of these were higher or lower. So you kind of have a more complex geometry right there, right? So I can take these and I'll import them, and I'll actually import them both at the same time, so I can set multiple curves. And I'm going to break them up. I'm going to use a list item. Now, a list item will just give me one of those, but I can also come into here and say, add another output. And so now I have these split up into several of those. And I can also add one in the negative direction. That's going to be the same since there's only 2 items in there. But this is the first item in the list. This is the last item in the list. That's useful if you had 15 of these, but you just wanted the first and last. That's a quick way of getting that. We'll use it that way. Okay. So I can set it up the same sort of way. I can say divide, and I can even do it where these happen at the same time and then divide them up, so you had separate lists afterwards if I wanted to divide them by the same number. So let's say I wanted to divide them by like 100 or something like that. Now you can see that this is a tree, because then I have 2 items in the list that each have 100 points, and this separates out into different lists. Oh, actually, I can't do it like that because that gives me the separate list. Let's do it the way I had it before then. So this gives me 100 items in that one, or 110, I guess, and 110 in that list. Okay. So if I wanted to sort of create this pattern of fibers that was connecting between those, I can do that through simple sort of list operations, right? If I wanted to make that line like we were doing before, it starts to connect it in different ways. If I add that shift again, list, shift that. I can start to create sort of the aperture to which these things are winding, right? And you can see, because this is not regular geometry, this starts to make this almost biohazard type sign around that. If you had a perfect circle, it would be a perfect circular oculus between those. Right? So now the patterns that we had in that weren't perfect. They weren't repeating over and over again. So we were doing different things to sort of make those lines. So let's say we wanted to only do a different sort of repeating pattern. I'm just going to get the ends of that one. Now I could say, if I wanted to remove all the ones that were too long, that might be one way of doing it. I can get the length of these curves. Right? I can say, what is the bounds of that? So the shortest is going to be 35. The longest is going to be 48-ish. So I can say, okay, any of these that are smaller than, let's say, 42. It's going to give me a true false value for each one of those, of which ones that are smaller than or larger than. So that's when I can use my Cole pattern. So these curves Cole with this pattern. So these are all the ones that are longer than 42 units, whatever that is, inches in this case. All right, and if I change that shift, you'll see that more show up or disappear. And if I change this length, you can see it changes that threshold at which that works. So I could potentially use that to say, okay, I only want to put extra fibers in this area because that's where the links are longest and they need more support or something. Whatever. I'm making that up. But that makes sense. Now, if I wanted to, say I wanted to see which item was the longest or the shortest or something like that, I could use a very similar sort of tactic, right? I could get their length, and I can sort this list. Now, this list of links is what I want to sort, but what I want in the end is the length of lines that's sorted. So I can plug this in as that k value, which is our key that we're sorting, and it's going to give me a list of sorted links over there. Now, if I plug this length of lines in as the a values, those are going to sort in the same way. So and they're going to sort from smallest to largest. So if I say a list item right here, that's going to be the shortest line in that list. And if I say that, that's going to be the longest line in that list. So it enables me to sort of analyze and pull out different information that I want. Right? Now, this isn't exactly how we did it. All of these are just straight lines. What we were winding was a continuous line that went from point to point, so it happened a little different. So I'm going to introduce you to another sort of and you can see under this is under the, what tab is this? The sets tab. Most of the things we've gone over have been in this sort of list. We did the longest, shortest. Cross-reference is one thing that we didn't do. I should have showed that. Say we wanted to create some sort of connection of lines between those, and I'm gonna turn this way down to just have a few of them so you can see it a little clearer. 8. Say we just have these 8 lines. Now, if I wanted to make connections between those, we did the shortest, we did the longest list. Cross-reference is another one that's useful, and what that does is it's going to take this list and this list, and it's basically going to make a connection from every one of these to every other one in the list below it. So if I did this, you would see that now each one of these is connected to all of those. Now, if I turn that up a whole lot, it's just going to be a huge mass of lines because all of them are literally connecting to every other one. That's useful in some cases, and we'll show that with sort of arrays and things a little bit later. But that's another useful tool that you can use is cross-reference. And it also has other sort of things, like you can decide, let me turn this back on, to only connect to ones that are above or below it. So like if this number is 4 and this number is 2, it might not connect to it, but it'll connect to a 5 and a 6 or something like that. So you can look through that one and use it in different ways. But the one I wanted to show you was other ones in this list. So we went over longest list, shortest list, cross-reference. A lot of these we didn't go over, but maybe you can try out in terms of reversing a list, sorting a list we tried, list length. You can call out a specific item by its index. You can insert items into the list. Split the list we went over but didn't do. But one you might want to try is to weave a list. So say you want to take one from one list and one from another list by some sort of pattern. So if I had this is one list and this is another list, and then I wanted to set up a pattern in which I weave those together. So this is using another Boolean pattern. In this case, instead of true false, it has ones and zeros, which work exactly the same. So I can come in here and say 0, 0, 0, 1 as a pattern. And I'll set that to multi-line data just so it reads it as individual numbers and not just one big character. If I set that to the pattern, that's going to come up with a new list of points that I can make, let's say, a polygon. Let's turn these other lines off. So it doesn't look like much. Let me turn that up. So what that's doing is you can kind of see that this is the 0th one, and this is the first one. So the one that I plugged into 0 would be the bottom. The one that I plugged into 1 would be the top. So it's basically taking an item from this list, taking an item from this list 3 times, and then it takes an item from this list. So this list is much smaller, and this list is much bigger on the top. But it connects back and forth into a single sort of polyline. So it weaves those two lists together in whatever sort of pattern you need. So that also is pretty useful. Okay, so let's take a quick look at arrays. So arrays are just a bigger sort of list. Let me see, do I have any other? Okay. So say we wanted to make a 2D grid. You know, there's different ways of doing that. Obviously, there's grids that you can make like this sort of situation that are pre-built for you. I'm gonna make it through point values, just so I can show off some of the list management things. So I'm gonna make a series. And a series is basically, I don't know if we've used that yet. It gives you a starting number, it gives you the step size, and it gives you the number of points you want. And what this basically gives you is a list. A list of numbers that start at 0, step up 1, and have 10 numbers total. So I could say I want it to step a different number. I want it to be steps of 10, similar things like that. Now, another way that you can do that instead of a series to make a set of numbers, you can use a range. Now, a range is kind of the opposite. Instead of adding numbers up, it sort of breaks numbers down. So in this case, you would say, I want a domain, so it might be 0 to 10, and I want that split into 10 separate numbers. So it'll give me all the numbers in between that. So those are very similar. You can do similar things with that. If you adjust this, it's going to give you a lot of decimals in there, things like that. So those are two ways of easily making lists of numbers. Okay, so I'm gonna come in here, and I'm going to make a series of numbers to use as an XY value for a grid. So if I say that this is going to be my X value and my Y value, then I should step over into a grid. So I can make a point construct point where I feed it an X value. This would be my X value. You can see it already makes a point with Y0, Z0, and this X value. Now if I plug in the Y value, it's going to change that as well. But what happens? Okay. we don't have an x and y value for each one of these. We only have, like, this is 0, 0, 1, 1, 2, 2, 3, 3, because it pairs these up in that list. So this is where a cross-reference really helps. So we can say this list and this list is going to be our x and our y. So now, if we look at this, it's going to repeat that over and over again. 0 through 9, 0 through 9, 0 through 9. So what it's doing is basically for the first 0 of y, this is y, it's going to go 0 through 9. Then it's going to y equals 1, x equals 0 through 9, y equals 2, 0 through 9. So it makes a point associated with each one of those. So that's what the cross-reference can be used for a lot of times, is to make these kind of like grid type systems. Okay, so I have this grid of points, right? And I'm going to make an attractor system. So if you're not familiar with attractor systems, it's actually a super common thing in Grasshopper. It's one of the first things that Grasshopper is used for, because it's actually super easy. You have a set of inputs that you measure their distance, and depending on how close geometry is to that input, determines some characteristic. Maybe we'll use a circle. So I'm gonna say make a circle at each one of these points, and let's turn it down. I want the radius to be 0.5, so they're just tangent. Okay, so what happens if I don't want them all to be the same, but I want them to somehow relate to some other geometry? So I'm going to put a point in here. I'll put it somewhere there. At this point, I can move around in space. Now, if I knew the distance from this point to every point in there, I could potentially change this radius of the circle to match some relationship to that. Okay. So let's get the distance. And it's useful when I'm typing these things. If I don't know the specific command that I need, just type what I think. And like I said, a list of things coming up is usually what I think it is. Like, if I'm looking for distance, it's going to be distance. But that's not always the case. Okay, so I get some distance, and I have a list of 100 points and their distance to this one point. Now, I can go ahead and plug this radius in, and it's going to give me some wild stuff, because every one is going to be sort of tangent to each, or have the radius of that point, so it's going to be tangent to wherever that point is in space. I'll move this around. You can see that sort of like updating. So it's an interesting sort of pattern, but it doesn't really allow me to see what that's doing. So I want to somehow scale these down, and so I'm going to remap those. So I want to see how big some of these things are. I'll get the bounds of this. And I know the smallest is going to be 0.6 and the largest is going to be 6. Okay? So I can remap the numbers. Say these numbers are what I'm going to remap. This is its current domain. And I want to remap it from something small, 0.05 to 0.5. So I need to make a new domain. So if this is 0.6 to 6, this new domain is 0.5 to 0.5. Okay, so all these numbers should be remapped to that range. So if I plug that in, you can see that they're more scaled appropriately so they don't overlap. And if I move this around, all of them sort of update depending on how close they are to this, right? So you've probably already seen a version of this in Grasshopper before, like some sort of facade that's changing or whatever. Attractor points are super common, so it's something you should know, but don't overuse too much. Okay, so we have this. Let me turn these points off. Let's see if we can color code them, right? So we want some color spectrum that represents these radii. So I'm going to say we need a custom preview. Preview. These are going to change to some color. And I don't want the same color, like all of these are pink, but I want those values to affect it. So I'm going to use a gradient. I'm going to set this gradient to some other sort of preset. Maybe I'll use the red to blue preset. And so this is very similar. It'll pick like a lower limit and an upper limit, which is kind of like a domain. And whatever that value is in within that, it's going to fit in the spectrum and give you a color, right? So if we set the lower limit to be 0.5 and the upper limit to be 0.5, then this value should change all these per that color spectrum. So you can obviously see that this one is the highest value, and one of these down here is going to be the lowest value. All right? Let's crank that up and add some more points to this. Okay, great. So we have an attractor set up. They're somehow adjusting. If we wanted to, we could even put a surface on that. Make them solid. So those colors are a little more apparent. Okay, so let's see what else can we do with that. We can give it multiple attractor points. So instead of just that one point, if we had multiple, we can sort of put those in space, right? Now, if we just plug this into the distance, that's going to give us several distances, but you can see it looks like just one big gradient like this, because this is a list of points and this is a list of points. So basically the first item in this list, wherever it is, you can see this one's really small because it's measuring to the first item in this list. The second item is measuring to the second item, wherever it is. And so like these down here look slightly off per this other thing. It's not until it gets to the last item that it does the rest of them, right? So we don't want that. We don't want to measure the distance to all of them. We actually want to see whatever's the closest one. So I'm going to say closest point. And then I'm gonna say these points are what I'm gonna measure, and I want to measure also to these other points. So you have points to search from and cloud of points to search in. And so I want a value for each one of these, which is each one of these up here. So that's what I want to be the P. If I plugged them in the other way, I would get basically five values if this one went into the P. But I want the sort of 625 values to come out. So a value for each one of these. And that gives me a distance, but I have the same number, 625, and it'll tell me what the distance is to the closest point. So I'm gonna hit Control Shift to move this distance down to this distance. and let it update. It's probably a little slower because I made those surfaces. Let's take those back to circles just to make it a little. See that this is taking 3.1 seconds to run. So I won't use that for all the calculations. Okay. So you can see that these things are working where all of these that are around here are the distance to this, and all of these around here are the distance to that, right? So each individual point has its own sort of hotspot, if you will, right? Okay, so what else? We don't have to necessarily use points. We can use any kind of attractor. It's all built on distance, so we can get a distance to a curve. Some stuff mushroom. Not sure what's going on there. Okay. So I'm going to input this curve. Let's turn these off. Okay, now if I use that, I'm going to use a similar closest point. I'm going to use curve closest point. So that's the curve. These are the points. See if I can unplug some of these things. Plug the distance back into this one. And spread this out so it's not so jumbled up. You can see like this was a single distance. Group that. This was the other sort of input with multiple points. Now I'm testing out a curve. So the curve will give you all of these points along that curve, but more importantly, it gives you that distance, which is what we want to use. Okay. So with this, you can see that this gradient updates, right, along that curve. So you can see it's continuous. All of these are red. These are blue. If I move any of these points or the whole curve itself, those sort of update. Now, I can also use those not only to create the sort of like scale of these circles, but I can use it, since we have this 2D grid, I can make a new surface from all of those points, right? There's an X and Y direction. Each one of these, you can make a surface from a grid of points. So I can sort of map those more three-dimensionally in some way. So if I say surface from points, if I feed in all the points, and this has to be in a grid. If it's not in a grid, it'll give you a problem. You can't just have random points in space and it'll make a surface out of this. But if you have all the points and you tell it the number of points in one direction, it'll be able to sort of organize them for you. So I'm saying if these are all the points, and the number of points in the direction is how many times we're dividing that series up, 25. So I can make that. Now, that's just a flat surface, but we can give those points some sort of value associated with that sort of attractor geometry. So if we say those points are moving, I'm going to move this point. Right now they're in the Z direction, which is actually what I want to keep, the Z direction. But I want to set it as some sort of relationship to this distance. I plug those in there. I end up with a surface. You can see the valleys are where it's closest to the point, and the sort of peaks are where it's furthest away from this point. Now, this is a new sort of surface, but it's also a sort of graph, right? It tells me where it's furthest away and where it's closest. And can generate some interesting sort of geometries through that sort of relationship. Okay. All right. Let's do one more example. Sort of going through a different type of array. So this is it's a little jumbled up. I think it's a little cleaner in the example files that I gave you. Okay, so instead of making a 2D array of this, how would I make a 3D array? Any question or anybody? Anybody listening? Giselle's the only face I can see. What? Okay, so if we're making a 3D array, it's not too different, right? It's, you know, if we're sort of using a cross reference to make a 2D array, then the same would hold true if we're making a 3D array. Oh, let me copy that. Except we just need a third cross reference. So now you have this nice grid of points. And we can use this to do some interesting things. So I'm going to make some sort of curve. Switch to top view that goes through the middle of this. Whatever, it doesn't have to be specific. And I want to sort of move it up as well. So let's take a couple of these. Trying to make it not super uniform. Okay, we'll go with something like that. That is kind of a three-dimensional curve in space for whatever that's worth. Okay, so we're gonna bring that curve in, and I want to set up some sort of voxel system, and a voxel is just a 3D pixel in a way. We've set up our grid for what that is, and I want to determine some relationship of those voxels to this curve. Okay, so I can use a similar sort of strategy for getting the distance. I can say curve closest point to here. going to give me those distances. Well, first of all, let's make our voxel system. So for each one of these, I can make a box. And I want it to be, let's use a center box. Now, I want it in a specific size. Let's make it, let's see. Let's do it this way. I think in the example, instead of using a series, I used a range. Because I want to divide up a specific space. So I was going to say this one, 0 to 25. And I think I had a... Okay. So I can say I want more or less. And depending on how many things I want to divide it by, I have some freedom to do that. And don't want to turn it too big. Hopefully I didn't crash it. Don't crash it. You can easily, since this is sort of cross-referencing all of these, if you go too big, it's making a reference to all of them again. So I'm going to use something like 12. But you can see, or it may be tough to tell, these things aren't exactly the right size. It's close to it because it's close to half. So if this is dividing up by a certain number of points, then this is going to be in relationship to how many divisions you have, and then the x and y values are going to be sort of split in half to give you half of that box size that fits within that. So if we have some relationship between this, we can change the box size and try to get it always fitting next to each other in the right way. So let's see what that might be. If we have this number, let's get rid of these. This number 25 divided by this, which is basically what that range is doing, will give us how big each one of those boxes should be total. Right? And then if we're saying that we're making the point from the center, then it's going to be half of that this way and half of that way. So let's multiply that by 0.5, or we can look at what it does if we don't do that. This becomes x, y, z, that it actually is twice as big as it needs to. If we set it to 0.5, kind of makes it the right. It's radius versus diameter sort of situation. Okay, so now we have boxes that are scaling to fit. Oh, can't go to 0. Scaling to fit whatever number of voxel sizes and grid size that we're making with that. So that's good. So it's sort of parametric, and it's always sort of updating with that. Okay, so now we have these boxes. We want to somehow determine when to make these boxes and when not to make these boxes by that curve and the distance to that curve. So the same sort of thing, we have the distances down here. We can set some sort of threshold like we were before, like where were we doing that before? Like if it's smaller than a certain length, then get rid of it. So we can say if this distance is, well, let's see what those distances are right now. These distances are going to be between 0.1 and 16. So let's set up they're smaller than this distance, smaller than 10, or let's set the maximum to be 16, so we're somewhere closer. So if this distance is smaller than some threshold, we're gonna get rid of it. We're gonna pull this point out of the list and not make that box. Let's see what that does. Okay, so now we have some sort of voxelization system that can take our geometry and convert it into these boxes. And we can say at what threshold this is happening. Yeah. So, not that this is an architectural system, this is actually pretty abstract, but you can start to think of ways of using some of these tools to make architectural systems, right? If this line is somewhat like a circulation, and these are the spaces around that circulation, we can start to build sort of interesting ideas from that. Okay, so same sort of thing. Let's look at that with some sort of visualization. A custom preview. And I'll just use a swatch for this right now. Okay, that looks fairly good. I'll go back to shaded. Now in the let's take a look at the assignment real quick. In under data management, I have these exercises that I've given you a grasshopper file. Let me see if I have exercises. Okay, so I've given you some prompts for how to use this. So in one case, let me turn this off. We've done variations of things that you can use to do this. I've given you a bunch of lines, and I've said I want you to find the length that's closest to the average. So simple sort of problem to solve. You have some goals, you have some inputs. How can you sort of like look at this line, understand what the average length is, and find a line that has the closest length to that average, right? Another one is I want you to create a 2D grid of circles like our attractor point setup that we have with multiple attractors. And I want you to get rid of about half the circles whose distances are the largest and color code them in a similar way to how we did it. Okay, these shouldn't be too difficult. Don't spend more than an hour on any of these. You can probably do it in less time than that if you followed along and are understanding things. The last one is with that voxel grid. Remove the voxels that are closer to the guide curve, pretty much the opposite of what we did, and color code the voxels by their distance to the curve. Now, with both of these where you're removing items, you might find that the color does some weird stuff. Like if I go back to that if I go back to that, I'm not gonna show you what I'm doing because I want you to figure it out on your own. But if I were to put some sort of color associated with these, now if I turn that up all the way, so I'm not getting rid of anything. I turn that up all the way. It's a pretty good sort of heat map scenario of that curve, right? As soon as I start getting rid of any of these things, the colors get all messed up. Why would that be? Well, I'll give you a hint. We now have the same amount of colors being fed into this, but a different number of boxes. So what happened when we had a different list length with the lines? And it would try to connect lines, multiple lines to the same point. Well, that's essentially what's happening here, is trying to make the same box different colors. The length of colors and the length of boxes is different. So ideally, if you want to keep the color consistent while removing boxes, you'll need the same number of colors as you do boxes. That's going to be my hint. You can work through how you might do that. Okay. Any questions? No questions. I'm going to stop the recording.